In this course, till now we have seen 5 different representations for regular languages, and they are DFA, NFA, NFA with epsilon transitions, regular expressions, and regular grammar. And today we are going to look at different DFAs for accepting the same language, and they are called equivalent DFAs. And through examples, we will try to understand how can one construct a minimal state deterministic finite state automata for a given regular language. So what is the DFA equivalence and state minimal state automaton, and that is the topic for today. So we can start with some examples. So here is a DFA given. A is a DFA, and the question is what language is accepted by A. Here you can see that only 2 states are there, and both the states are final states. So you see it is going to accept all strings because both are final state. Doesn't matter where you stop. Now look at another DFA, B, having a single state. What is its language? Easy to see. It's again the same language, the set of all strings over AB. So now we have 2 DFAs, A and B. They are equivalent. Equivalent in the sense they both are accepting the same language. And here we can observe that what we did is equivalent states are collapsed into a single state to obtain this DFA. If you want to see how can one obtain a minimal state DFA, then it's a kind of finding equivalent states and then merging or collapsing them into a single one. Later we can see what are equivalent states, maybe in the next class. And so what we have seen is 2 DFAs, A and B, are said to be equivalent if and only if the language of the first DFA and the language of the second DFA are same. So that is DFA equivalence. And in this example, we know that B is a DFA with fewer number of states. A has 2 states and B has only 1 state. Let us move on to the next example. Here is a DFA given, A, and can you identify the language represented by this DFA? Not that no loops are there coming back to any one of the first 5 states. So you can only go through one of these paths and reach here and stay there. So if you carefully observe, you can see that any string of length 3 will take you to this state and you will stay there forever. It doesn't matter through which path you reach into Q5. So all the possible strings of length 3 will take you to Q5, and from there you are staying there in a final state. So what is accepted is, if you want to find what language is accepted, then is the set of all strings with the length greater than or equal to 3. So that's the language. Now for this, maybe you can have a DFA B. So what is the language of this DFA? This is having a fewer number of states, and it is very easy for you to see what language it is. Any 3 letter will take you to this and you are staying there. So same as this language. So here again A and B are equivalent DFAs, and B can be thought of as obtained from A by collapsing equivalent states. Here these states are found to be equivalent and collapsed into this state, and these two are again found to be equivalent and collapsed into this state. Please don't worry about how we can identify the equivalent state and how can you collapse. That we will learn in the coming in the next lecture after discussing equivalent states. So here again B is a DFA with fewer number of states. Let us move on to the third example. So here is a DFA A given. Can you find what language is accepted by A? It's not difficult to see that the language is, how will you reach into Q3? You can see that in order to reach into Q3, the string must contain the substring ABA. If ABA is there, you will reach here. And if you observe, you can see that that is exactly the logic here. ABA will take you here. If you read an input, if the input contains ABA, then the moment you finish processing ABA from the string wherever it is, you will reach into Q3. If you are not able to see it now, see it offline and please try to understand what is happening. And now take it as granted, ABA, the presence of ABA is taking you here. And you note that once you reach into here, it doesn't matter to which state you move. All the states are final states. So once you reach into this part, you will accept. So the language is set of all strings over AB said that ABA is a substring in the input string X. That's the language. Now I know you got an equivalent DFA with a fewer number of states because all these three can be collapsed. And so what we did is, so this is the language of this is same as this language because what we did is we collapsed these three into a single state. So find equivalent states and collapse, that's what we did. Again, how we find is a different issue. Suppose someone is telling you that these are equivalent, then what you do? Collapse all this into a single state and all the transitions then have to be defined back to itself. That again we will discuss how to collapse. So equivalent states you have to find and collapse. That is what you can do to find an equivalent DFA with a fewer number of states. Here again B is a DFA with fewer number of states. Now move on to another example where we can discuss an NFA to DFA conversion. Here is an NFA given. The language is the set of all strings over AB with the third last simple as B. Here you can see that if you accept, then you are in this state. Okay, sorry, this transition is not there. That is a mistake, and so consider this as not present. Okay, this transition is not there. And that was a mistake. So sorry for the mistake, and we should not have that transition here. Then it is wrong. Okay. So assume that these transitions are not there. Then it accepts this language. And sorry for this mistake. Now, if you apply the subset construction algorithm on this NFA, you will get an NFA in that there will be 16 states, because you know that in the resulting DFA the states are the subsets of these states. Here 4 states are there, so 2 raised to 4 subsets from null set to 1, 2, 3, 4 are there. Sorry, 1, 2, 3, 4. So 16 states are there, and this is the resulting DFA. And Maybe you can check it offline whether it is correct or not, but believe it, it's correct. So out of the 16 states, you can see that only 8 states are reachable. All these red states are non-reachable from the initial state. The initial state is set 1. From there you can see that all the red colored states, here 8 in number, are non-reachable. So we need not have to retain the non-reachable states in a DFA. How we obtained it is by applying the algorithm. We obtained our DFA with the 16 states where only 8 states are useful or reachable. So what you do, you just throw away all the unreachable states to minimize the state. So you are getting this DFA with only half the states, and that's again 8 state in this DFA. So here again we obtained a DFA with a fewer number of states from the 16 state DFA. This is the DFA, this is N of A, and not that this transition is not there, that is happened by mistake, this is not there. And then this is the equivalent DFA, and from the equivalent DFA you can throw away all the unusable states to obtain a DFA with a fewer number of states. And what we did is all the non-reachable states are removed. And this is a classical example used to illustrate that NFAs are exponentially more succinct than DFAs. For example, here you have only 4 states, or nearly 3 plus 1 states. 3 is the number of symbols from the right that we are counting. And here there are 2 raised to 3 states in the DFA. And later you can see that if you try to minimize this, you cannot. So this is a classical example used to illustrate that NFAs are exponentially more succinct than DFAs. So that's a different topic. I just wanted to mention it here. So here what is important is this, from the NFA, this transition is not there. We obtained a DFA where 8 states are non-reachable from the start state. These are the states non-reachable. Just throw away all the non-reachable state and you are obtaining the equivalent DFA with a fewer number of states. So we have seen 2 different techniques to reduce the number of states. The first one is find all the equivalent states and collapse them. That is what we saw in the first 3 examples. And second method is find non-reachable states if there, then just throw away them. Then the question is, then how can be there non-reachable states in a DFA? It can be there if you are obtaining the DFA automatically using the subset construction algorithm. So after doing that, you can apply this technique to reduce the number of states. Now an interesting question is, given a DFA A, can we automatically find the minimal state DFA equivalent to A? So we want to find the DFA with the minimal number of states. The minimal number of states, that means the one with the least number of states to accept the same language. It would be nice if we can do it. Given a DFA that may be having any number of states, maybe a large number of states than what is actually required. Then the question is, can you automatically reduce the number of states to the maximum possible level? So is there exist an algorithm? It would be nice if the answer is yes. And the answer is yes, because there exists an algorithm to find the equivalent minimal state DFA from a given DFA. Not that equivalent means accepting the same language. And if you want to see more about the algorithm, we will discuss this later. But basically, there are these two steps in the algorithm. The first step is remove non-reachable states if any is present in the DFA. That is the first process. And after that, what you can do is find all the equivalent pairs of states and collapse them. And the first step is very easy. You know what you can do. The second step, we need to first find equivalent states in a DFA. So in the next class, we are going to define an equivalence relation over the set of states in a DFA which can be used to identify the equivalent states. So in the next class, we will be recollecting equivalence relation from relations, and after that we will define an equivalence relation over the set of states of a DFA, and using that we will derive an algorithm to minimize the number of states in a given DFA. Thank you.